Hello, this is Jonathan Engelsma. This is part 7 in our tutorial on learning how to program in C. This lesson is on strings and pointers. First we'll look at strings in C, then we'll look at pointers in C, and we'll wrap up by looking specifically at function pointers in C. Let's talk about strings first. So in C, we've seen that a car represents a single character. Hence, we can define a character C to hold a single value, a single character value. Well, in C, we represent strings as arrays of characters. In the second example here on the screen, you can see the variable str, which I've defined as a character array, and initialized to the characters bye, and then a funny character, a /0. This forms or represents the string bye, bye. That /0 value represents the end of the string. Why didn't we just use the character value 0? Well, the character value 0 has an ASCII value of 48. You can confirm that by looking it up in an ASCII table. But we want a character with an ASCII value of 0 to represent the end of the strings. Hence we use the /0. In C, we refer to this value as the null character. Now in C, by using character arrays, we can represent strings, but we want to be able to represent variable length strings. So some strings might have fewer characters than others. Not all strings have the same length. So that is the significance of that null character, which we saw in the previous example. The null character represents the end of a string in C. So when we operate on strings, when we use strings to do comparisons, or we do concatenation, or we copy strings from one location to another, we're always going to use that end of string marker, the null character, to represent where a string ends. So we need to be able to look for that, and it's important that when we represent strings, we actually have that null character at the end of it. Now we also have some additional notation. So we can use the asterisk operator on the type to form what we call a pointer. So in this example, I can use a car star to refer to a string. So in the first declaration, I have a car str1 of 6 elements, and I've assigned the string hello to that character array. I can define a variable car star string 2 and have it point to that array. So string 2 is what we call a pointer to a character, or in this case, it's a pointer to the beginning of a character array, a pointer to the first character, if you will. But remember, we're going to use that null that null character to terminate the string. I've got a third variable here, car star string 3, str3, and notice what I've set that to. I've set it to ampersand str1 sub 1. The ampersand operator is basically taking the address of what's on the right. In this case, what's on the right is str1 subscript 1. That refers to the second element in the array str1. And so str3 here points to a string containing the characters ELLO. So in memory, we can think of a car star str1, such as the one we saw in the previous example, we can think of the str1 here as pointing to a variable. So I've got car greeting defined as a 6-character array with the string hello. So when I have the declaration car star str1 equals greeting, it's basically a pointer to that previously defined character array greeting. if I assigned the expression ampersand greeting 3, you can think of that as a pointer that's pointing to the characters beginning at the second L in my original string hello. So in this case, the string pointed to by str1 would be the characters LO. And finally, the original string was of length 6, so that means the valid indices would be 0 through 5. So if we subscript or accessed or tried to access the 6th element, greeting sub 6, that's really the 7th element, and that is really unknown. If we do that, that would be actually an out-of-bounds indexed. So the C compiler and runtime is not going to check for that. So we really don't know what could happen there. It could be referenceable and garbage value, or it could be an invalid address and could cause our program to fault and to abort. So one of the things we want to do, just like when we work with arrays, we want to make sure when we're indexing character arrays, in other words, strings in C, we always want to make sure that our indexes do not go off the end of the defined array. Now we saw the /null. There's a number of different values that we can represent in a C string literal using the / syntax, and I've listed them out here. So I have a /a, which is an audible alert, and in general, if you look at the, and I guess another significant one would be a /n. We've already seen that when we use the printf and fprintf in previous lessons. There's a /tab, represents a horizontal tab, and we can also encode arbitrary ASCII character values using /NNN, which would be 3 digits representing the character's ASCII value in octal, or, as shown in the very last entry on this screen, /XNN, which would be a hex value of the ASCII value of the character. The C library, or the C standard library, provides us a bunch of helpful string manipulation functions. So we have a string CPY, or string copy, which allows us to copy one string into another. We have string dupe, or strdupe, which allocates memory, and we'll talk more about dynamic memory allocation in a future lesson, and makes a copy. We've got strlen, which computes the length of a string, and the way it does that is it walks down the characters until it finds that null character. We've got string cat, which lets us do string concatenation, and we got string toke, which lets us tokenize or break an input string into tokens. Now you can learn more about these commands on your Unix or Unix-like system by simply typing man space and then the function name on a command line shell. Let's talk about pointers in general. So we've already looked at strings in C, and strings are just one application of pointers in the C language, but we can use pointers in a more general way in C. And the purpose of this is that we can use pointers to effectively represent and refer to more complex data structures. And in a future lesson, we'll see exactly how this is done. We can also use pointers in C to pass data to functions by reference. So we've seen already that most data types in C get passed by value. The exception of that was, of course, arrays. And arrays are actually pointers. We just didn't tell you about that yet. But if I wanted to pass, for example, an integer or a character by reference, we would need to use pointers to do that. Another useful purpose of pointers in C is that we use them to work with dynamically allocated memory. That also is a topic that we have not yet talked about, which we will in a future lesson. And finally, pointers give us a way to more concisely and efficiently interact with arrays. To understand pointers properly, we need to think about the concept of indirection. Let's say, for example, you work at a company named Acme Widgets, and you need to buy a new MacBook Pro. Instead of contacting Apple directly and making your purchase, you're likely going to contact your company's purchasing department, and the people that work there, in turn, will contact Apple and make the purchase for you. So you're not contacting the vendor directly. Instead, you're working via the purchasing department. Pointers in C work according to this same principle. So you can think of a pointer as a variable that provides you an indirect means for accessing the value of a particular data item in one of your data structures. So we use the asterisk operator to define a pointer in the variable definition, similar to what we've already seen in the case of char to define strings. And we can use the ampersand operator to get the address of a variable that we've declared. And we've actually seen this syntax already as well. You'll recall that when we pass arguments to scanf, variables that will hold the results that have been processed or parsed by the scanf function, we needed to put ampersands in front. And at that time, we told you just to take that on faith, and later we'd explain it. Well, that's a situation where we're passing those variables by reference, so the function can, in fact, update their values. So in effect, a pointer variable holds the address of the data item it points to. So you can think of a pointer variable as a reference to a piece of data. So let's look at an example. Here, I've defined a variable count which is initialized to the integer value 99. This allocates actual memory to hold an integer, and an integer on most modern machines today is going to be at least 4 bytes. The next variable, lowercase p count with a capital C, represents or defines a pointer to an integer. So the star in front of the p count sets this up to be a pointer. So this does not allocate an integer value per se. Instead, it allocates enough space to hold a reference or address of an integer. Now, in this case, we've initialized the variable p count to the address of count using the ampersand operator. So, one way to think of this is to say that p count points to the integer count. In the very last line of code, we use the star operator to represent what p count is pointing at. So we have count equals star p count plus 1. So in plain English, what we're doing is we're saying assign to the variable count, which is an integer, the value that p count is pointing at incremented by 1. Well, what is star p count? Well, p count was set to the address of count. So star p count refers to the integer count. So what we're actually doing here is incrementing the variable count via the pointer p count. So we can visualize this as follows. Here we see p count is not an integer type, it's actually an address or a reference, and it refers to the integer count. Initially, before we do the increment, count holds the value 99 from its initializer. When we execute the last statement in this example, then the count value is overwritten by 100. And interestingly enough, when we're done here, if we dereferenced star p count again, we would have 100 because it points to the integer count which holds 100. We can also use pointers to pass values by reference to function. So here's a very simple example. I have a function defined with the name swap, and it takes 2 arguments, a pointer to an integer and another pointer to an integer. So it takes two pointers, both of which point to integers. In the body of my function, I simply swap these values. So I assign to a local variable called temp star v1, which says assign to temp the value that v1 is pointing to. Then I assign the value that v1 is pointing to. So notice the star v1 on the left side now gets replaced with whatever integer value that v1 is pointing to. And I assign that equal to whatever star v2 is pointing to. Finally, I take whatever v2 is pointing to and I assign to that temp, which holds the original value of v1. So in my main routine, I define two integers, I, which I set to 1, j, which I set to 2. I then print those values out to show you what they are, so I should see an I equal 1, j equal 2. Then I call swap, but notice I precede the parameters I and j with the ampersand because swap expects a pointer to an integer, not an integer. If I left those ampersands off, the compiler would complain because it's expecting pointers. So I get the address of the declared variables I and j by using the ampersand operator. Because I'm passing the pointers, the values or the updates that are made in the swap function actually will be reflected in the I and j values in the main routine, even though those variables are defined within the scope of main. So the output to this program would be as follows. You see I equals 1, j equals 2 after the initialization. So the first printf statement prints the first line. Then we call the swap method, and when I print out those values again, we can see once again that they are swapped. So this is an important use case for pointers, to be able to pass variables to functions by reference instead of just by value. Now the other thing we can do in C is we can have pointers to functions. So in C, we can define a function to a pointer by using the syntax shown here. So the name of the function pointer is going to be in parentheses with a star, and that's followed by a list of 0 or more arguments, comma delimited arguments. So in this case, I have a function pointer that points to a function that takes a character pointer and returns an integer value. So let's look at an example to make this a little bit more clear. In this example, I've got a function defined at the top called myfancyStringlen, and it takes a character pointer str, or character string, and it returns an integer, and then it does some stuff. The main routine defines a string, hello, and it also defines a function to a pointer. The name of the variable is myFunPTR, and the function that it will be pointing at is expected to have a single input argument, char star, and a return value of int. The very next, so that's the declaration of my pointer to a function. In the very next line, I actually assign a value to that pointer. So the declaration simply gives me a reference to a function. It doesn't assign it to anything. So the next assignment, I simply take the name of the variable, which is myFunPTR, and assign it equal to, and all I have to do in C at this point is specify the name of a function that has the same signature in my function pointer declaration. So in this case, it's my function with the name myfancystrlen. The next thing I do is I invoke that function. To invoke a function pointed to by a pointer, we use a syntax that's analogous to the declaration. So in this case, I use the name of the function pointer inside a parenthesis with the name prefaced with an asterisk, followed by the arguments. In this case, it expects a char star argument, so I pass greet. So in this case, when I invoke that function, we'll see the message print out, please stand by, I need a cray for this one. Then it will return the string length of the string I sent it, which in this case is 5 characters. So I will expect this program to then print out a 5 and then terminate. Now, why might you use this? Well, there's a number of reasons for this. Imagine you had a program that has a sort algorithm, and imagine that it can sort all kinds of different items because the basic logic for a sort algorithm is the same no matter what we're sorting. Where the differences come in is how we actually do the comparison when we're looking at the collating sequence of the items that we're sorting. So one of the things I might want to do is have a sort function that sorts any kind of data, perhaps it's an array of pointers, but I want to have a comparator. I want to have a function that's very specifically defined for the specific type I'm working with. So I might define those functions, and I might pass them to my sort algorithm as input. In other words, I can pass a pointer to a function to my sort algorithm, and I can reuse that sort algorithm in a lot of different contexts. Well, we've covered a lot of material. Why don't we look at some hands-on code samples and get a better understanding for strings and pointers in C. Let's look at some sample code. I've got several programs that I've already written to demonstrate various concepts that we've just discussed. My first example is called strfun, so let's take a look at the code. Yep. String fun. And in this particular program, let's take a look at the importance of having our strings terminated with a null character. So here you'll notice I've got a character variable C assigned to the value or the character X. I've got an array of 5 characters called greetings or greeting, and then I have another character array farewell, which I've set to the string by. Then I have 2 printf statements. And so if we want to print a string, we're going to use the %s in our string format, or our format control. And in this case, I want to print out the string greeting. And the question here is, what is going to print when I run this? The second print statement prints out the value or the address, so it prints out the string that starts with the address of C. So this is kind of curious code, but to understand what's going to print, we really need to pay attention to this concept of null termination characters in C strings. Let's go ahead and just run the program, and then we'll discuss the results. So we'll run this, and notice how we've got hello bye on one line, so that's the output of the first print statement, and the string X hello bye on the second line. So that's what was produced by the first or the second printf. Now you might be thinking that's not exactly what you expected, but let's look at the code again and see if we can understand this. The first one prints out greeting, but notice how we've defined or how we've initialized that array greeting. We've assigned it the characters HELLO, but notice we've omitted the null character on there. The very next variable is a string array farewell, and it's set to BYE. So when the C compiler allocates the memory for these local variables, it allocates consecutive locations in RAM. So we will have an X, and at the next address we will have H, then an E, then an L, then an L, then an O, then a B, then a Y, then an E. So if we do not specifically put in those null terminators, the string is going to run in with the next string. These routines, including printf, are going to keep printing until they hit that null. That's why in the first one we got hello bye, because it starts printing at greeting, which is starting at the H, And the last one was the address of C, which is the first character, and it printed all of the characters in all three of the variables here. Now you might be wondering why it stopped at the E in by and why it didn't keep going. Well, that's because when we define a string literal, such as we've done here, bye in double quotes, then the compiler is smart enough to put that null character in there automatically. So that one is defined with a null. So that's why when we print the last one, we actually get the characters up to the E and by and no further. So if we wanted to do this in a way that we got the output we expected, we'd probably want to put a null character after the O in the hello array, and we'd probably want to increase the size of that by 6 to accommodate for it, and we probably wouldn't want to print the data that's starting at C. So that last print statement there is probably a little bit pathological. Let's look at another example. I've got a function or a program called StringFun2, and this program will help us understand a little bit better how that ampersand operator works when we're dealing with pointers and arrays. And we'll also look at some intricacies of the size of operator that we've mentioned already. So I have an array greetings, and here I have added the null, and I have made it length 6 so it accommodates it. Then I've got farewell set to the string by exclamation mark, and remember the compiler puts the null in there automatically. Then I have two character pointers, str1 and str2. The first one I simply set to greeting. Remember, greeting is a character array or a string, but we know that really an array variable in string is really a pointer pointing to the very first element in the array. str2 I've set to the address of greeting sub 3. Greeting sub 3, since we're 0-based with our arrays in C, actually is pointing at the fourth element in the string array greeting. So it's actually pointing at the second L in hello. So the very first print statement is going to print out greeting, and we know that greeting points to a string hello, which is properly null terminated, so we're going to expect it to print out the word hello. The second printf statement prints str1, which is simply an alias to the first, since it's a character pointer that points to greeting, so we'd expect hello to print there as well. The third printf statement is going to print out the string starting at str2, which we've set to ampersand greeting 3, which we've already said is the second L in hello. So what we're expecting to print there is LO, just the two letters LO. So let's go ahead and run this and see if those print statements do exactly what we expect. And sure enough, we've got hello, hello, and low. So far so good. Let's look at the remaining code in this program. So these last 5 print statements use the size of operator. So the printf in the first one says size of greeting is, and then we send it the value of size of greeting. Well, what is greeting? Greeting is an array, and it's got 6 characters. So this is going to return the value of 6 because it has 6 bytes, 6 1-byte characters. The next example, farewell, is also an array. So what are we going to get here? Well, it depends on the size of that array. I believe it will return 5, but we'll see, because there's 4 bytes for the actual string itself, and I believe the compiler is also going to allocate a null, but we'll check that when we run it. Now the last 3 are kind of a trick question here. What are these going to produce? We pass in the variable str1, which is a pointer to car, and str2, which is a pointer to car. And then the last thing, ampersand greeting 3, what is that? Well, it's referring to an array, but remember it's an ampersand, so it's really just giving us the address or a pointer value. So size of, in this case, is operating on pointer variables. It is not operating on an array, a statically allocated array, or even a dynamically allocated array. It's simply referring to pointer variables. And so the answer, what this does, is going to vary on the machine, but on most machines it's going to return the number 4 because that's how long the pointers are on most machine architectures. So the last values are not going to return me the string lengths or the size of the arrays. They're going to return me the size of a pointer variable, which in fact is 4. So let's go ahead and try it and see if this works out as expected. And we got 6 for greeting, 5 for farewell. So indeed, it allocated the BYE exclamation mark. That's 4 characters plus the null character gets another 5. So that was 5. And as explained, the last values, the last 3 values were 4 because those are the size of the printers, the pointers. Let's look at one more. Actually, let's look at a couple more. So let's look at string fun 3. And this particular program shows us the string copy routine in action. And we've got a couple of variations on string copy. So it's stry, cpy. We actually have a string copy and we have a string n copy. The first one, which we'll look at first, copies the value on the right into the array or the string array on the left. So this is my farewell here is my destination and greeting is my source. So greeting points at an array hello, which is properly null terminated. And farewell points at a yet larger array that's initialized to the string literal by concatenated a bunch of times, followed by an exclamation mark. So what I'm expecting here is that after this routine is done, and remember we're passing pointers to string copy, they're char stars, so it's passed by reference. So when I do the printf here on the bottom, I'm expecting the original contents of greeting to be copied into the array farewell. In other words, the string bye 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 is going to be replaced with hello. Now some of you that might be more observant might have said, well, he's got an array of 5 for greeting, but he's actually setting it to 6 characters. Well, let's see what the compiler does with that. Okay. All right, so notice it says excess elements in array initializer. And so it did flag this as a warning. But the program would still actually run because there is a null. And so it did exactly as we'd expected. But we really should make sure that we don't put more characters in an array than we've defined it to. So we'll bump this up to 6. Okay, and it won't have any material effect on the program itself. The warning has gone away, and the program still does as expected. Let's take a look then at the other version of string copy. So we'll comment out this line, and we'll look at string ncopy. What string ncopy does is exactly the same thing, only the third argument here specifies how many characters we want to copy. So what it's going to do is it's going to copy until one of two conditions happens. It stops after it's copied 2 characters, or it detects the null character. So in this case, hello contains, or greeting contains more than 2 characters, so it's going to copy the first 2 characters of greeting, which is H and E, into the array farewell. But note that string copy and string ncopy do not copy the null character. So in this case, let's see what happens. Okay, so you'll notice that the first two characters of greeting got copied into the farewell array, but the null character did not get copied. So we end up with HE replacing the original BY, and then everything else remains intact, producing the string we see here. Let's look at one last example. I have a program called StringToke Demo, and this program uses file operations, and it uses a function called StringToke. StringToke is a useful function in the standard string library, and it lets us tokenize an input string. So this program is going to open a file called testdata.txt for reading, and it's going to read it line by line. You'll recall that's what fgets does, and it reads it into a buffer, which is a char array. And remember, fgets reads until it hits a line feed. Now, one of the things fgets does is it's not going to necessarily null terminate the string, so we need to make sure the last character that we've read is null. So the way I'm going to do this is use the string_len function. So string_len returns us the length of the buffer, and so I'm going to set the length -1 because we're 0 offsetted to 0. I'm going to increment lcount, which is my line counter. Then I go into a loop, and what I want to do is I want to tokenize that line. So I want to break out all of the tokens on that line. In my delimiters, I'm going to determine tokens based on the space character, the tab character, and the new line character. So basically white space. So this StringToke says take this string buff and break it into smaller strings, and the delimiter when I want you to break is going to be any one of these characters that show up in the second argument. So the very first time I call StringToke, I'm going to pass in the array and the delimiters, and if I get a token, so if there is a token left in that string, I'm going to get a reference back or a pointer back to a non-null value that represents that data. So toke is defined as a character pointer. So if toke is non-null, I know I got at least one token, so I'm going to go ahead and print out that token using printf, and then I'm going to try to get the next token. In this case, I'm going to call StringToke again, but the subsequent times after the initial time, I'm always going to pass null. And so this is an interesting function because the C library actually remembers the string that we use the very first time, and it remembers it keeps track of a pointer of how far it's processed that string. So when subsequent calls come in with a null, that tells the C library that we need to use the previous data that was left over from the initial call. So this is basically going to walk me through the string line by line, and it's going to call StringToke until we run out of tokens on that line. Then I'll break out of this inner while loop, which prints out each token on each line, and I end up back in my outer while loop, which goes and reads the next line from the input file. That outer while loop, of course, is going to continue until we hit an end of file, and in that case, pointer, the value, the string we're getting back from fgets, is going to be null, which calls us to drop out, and we print out the number of lines read, and then we close the file. So let's take a look at what this program does when we run it. So before we do that, let's look at the input file. I've got a file here called testdata, and you'll see I've got 1, 2, 3, 4, 5 lines, and each one of these has a number of tokens on it. I've got some punctuation and other things, but remember the white space delimiter here is space, tab, and new line. So let's go ahead and run the program and see what it produces. And I will pipe it to more so we can, oh, I guess I didn't need to, but there were 6 lines read. There was a blank one, I believe, at the end. and every one of the tokens, so everything delimited by space, tab, new line, appears on a separate line all by itself. So I've basically broken this input file into tokens. Now this is a very primitive example of the first phase of a compiler, the lexical analysis that we've talked about in the past. So as you can see, there are many interesting functions that we can use to manipulate strings in the C programming language. And of course, we can find out more about these. So if I wanted to learn, for example, about string length, I can simply say man stringlen and find out all kinds of gory details about how that particular function works.